Technically, it's evening right now, but
Yeah, yes.
yeah. The screen is visible to you, right?
Yes, sir, it's visible.
Okay, good. So have you gone through the lectures 2 and 3?
So I only completed two only completed, three not started, sir, yet.
Okay, okay. Yeah. You should finish it soon because the deadline for submitting the assignment is coming very close.
Yes, sir.
Okay, then I will discuss some sample problems and then
Oh,
you can see. Uh, okay,
okay, sir.
yeah. So the presentation is visible, right?
Yes, yes, it's visible to me.
Slides are changing. Can you see?
Yes, yes, it's changing.
Okay. Let's start with one of these sample problems. First one is that choose the correct options for the following statements. The polymer molecules are attached to each other with primary and secondary bonding forces, such as covalent bond, ionic bond, hydrogen bonding, and van der Waals forces. And statement 2 is covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur. So, which one of these is true or false? Can you tell me? Just analyze these two
Statement
statements.
one,
Yeah, statement 1.
statement 1 and 2 are both are true, sir.
Why are you saying that statement 2 is covalent bonds? This right here, as you can see, correct?
Okay, okay, sir.
Yeah, you can see here. These, this is the covalent bond, and here the secondary process such as hydrogen bonding happens. Okay.
Okay, sir.
Yeah. Then the next question is the is the following sequence correct or not for dissociation energy? Covalent bond, ionic bond, hydrogen bonding, dipole forces, and van der Waals forces. Is it correct? Like you can see the arrow is pointing the other side.
Okay, okay, sir.
Like
Mm.
what do you
Yes, yes,
think? Like
correct,
is it?
correct, sir.
Yeah.
Distance
So
energy is high in covalent bond.
yes,
Next, high in hydrogen bond, and then dipole force, and then van der Waals force is the
van
least
der
one.
Waals forces.
This
Correct.
is
Okay.
correct.
Yeah, because polymer structure's main primary force which forms the chain itself is covalent bond. So once the covalent bond itself breaks, the polymer structure starts
Okay,
disrupting. Okay, it will
okay, sir.
form small chains. Okay, you understood?
Yes, I understood, sir.
Yeah. And then next comes the ionic bonding. Ionic bonding happens when there are like ionic functional groups on the sides or at the ends of a polymer chain. Then it will form ionic bonds. And hydrogen bonding happens when the polymer chains are side by side, and then the hydrogen itself starts attracting each other. As you can see, this is a classic example of you can say polyethylene. Here, hydrogen is on both sides, and then it is
Okay, sir.
forming small bonds. Okay, and then we have
Okay,
dipole
sir.
forces, which forms because of the polarity. And then in the end, we have van der Waals forces, which is like the weakest force. Okay,
Yeah. Okay.
understood, right? Okay. Then here we have in which type of polymerization temperature is not easy to control. So what options we have here? We have solution polymerization, suspension, bulk, and emulsion. So which one of these do you
Bulk
think?
polymerization. Bulk
Uh,
polymerization.
why is that? Can you
Bulk
explain to me
in
why
bulk
bulk
polymerization we
polymerization?
need
Yeah.
in bulk polymerization process we have to heat in high temperature and mix regularly. Sorry,
Okay. And because of that, what happens?
stir up into stir regularly. Otherwise, the heat will not be distributed
Hmm.
properly.
Okay. So in that case, it is not easy to control, correct?
Yes, sir.
Yeah. So in that case, it is not easy. Next question we have for polydispersity index, which statement is or are correct? You can see that it is usually defined as the ratio of weight average to number average molecule, and usually it is usually one for monodisperse polymer or greater than one for actual polymer. It is used as a measure of broadness for molecular weight distribution. So can you tell me which one is correct for polydispersity index?
It is a ratio of the average molecular weight and the number of average molecular weight. It is
Hmm.
used to measure the broadness of a molecular weight
Okay.
distribution.
Yeah.
1 and 3.
But actually, if you read the statement too, even that would be correct. Why? Because for monodisperse polymer, what is a monodisperse polymer? A polymer which has like chain lengths of a similar size. One second. So here you can see that monodisperse means having chain length of the same size. Okay, but this is not possible in actual polymer. Correct?
Oh, okay, sir. Yes,
Yeah. So
correct, sir.
what happens is if chain length for monodisperse polymers, when chain length is of the same size, its polydispersity index will be 1. But that is not the case for actual polymers because actual polymers will be of varying lengths, and that itself will cause a great deal of variation in its polydispersity, because of which this statement is
Okay,
also
sir.
true. Okay,
Okay, sir.
understood?
Understood, sir.
Yeah. Okay. Next. Next we have what are other classifications of suspension polymer? Here there are three classifications. Which one do you think are true?
Bead and powder.
Yeah. So have you read about these processes? Bead polymerization and powder. Like this is basically what happens when suspension polymerization goes one way or the other. Correct? Like
Yes, sir.
bead formation happens when the monomers coalesce together to form the polymer chain, polymer bead itself. Okay. And this is the liquid phase where they are suspended. Okay.
Okay, sir.
Here you can see in a reactor, this is a stirrer agitator, and this is your H2O, that is the liquid phase. And then we have monomers which are suspended in this liquid phase, and an initiator. An initiator and the monomer work together to form the polymer chain. You can see this.
Okay, sir.
Okay, you can see right here that this forms a polymer chain. Okay, this is the initiator,
Okay, sir.
and it attacks the monomers, and then they form together the polymer chain. If the polymer chain which is formed is soluble in the monomer, then what happens? Can you tell me? Like, sorry, if it's not soluble in the monomer, then it would go for outer polymer. Okay, because if it's not
Oh,
soluble, then it becomes irregular and porous in nature.
okay, sir.
Okay, then
Okay.
let's move on to the next question. We have the polymer synthesized by suspension polymerization process on the following is. So basically, you will have to check out the synthesization processes of all of them and then find out which one of these is synthesized by suspension polymer. Uh, Here, in this case, polystyrene is the one which is synthesized by suspension polymerization. Here is the reaction scheme for
Styrene.
yeah, polystyrene. Yeah, here is the reaction scheme for synthesis of. Here is the reaction scheme for synthesis of polystyrene. As you can see here. Okay. We have a styrene molecule and one radical. And the radical then attacks the styrene molecule and it goes on to form the propagation step. And then on propagation, uh, the chain grows and then the polymer forms. And this is happening in a liquid phase.
Okay,
Okay.
sir.
Yeah.
Okay, sir.
Yeah. So next is again about the same suspension polymerization process. Here are some points. So, which one of them is incorrect? If you read through this, you can see that carried out in a continuous stirred batch reactor, initially monomers are dispersed in continuous liquid-based water in the agitator, or the size distribution, or the control of size distribution is not an important. So, if you can see that from point 3, you can find out the answer of this question, which is like point 3 is correct in case of suspension polymerization because the particles are formed in the range of 50 to 500 micrometers. Okay. Because
Okay,
of
sir.
this, we can know that control of the particle size distribution is actually an important issue in this process. Okay.
Okay, sir.
So the correct answer for this question would be this, but you can get a hint for this answer from this that since there is too much variation in the polymer particles, right? So
Yes,
that
sir.
itself is a big issue in forming the like in controlling the particle size distribution. Okay.
Okay, sir.
Yeah. I hope you are understanding this and taking some notes or anything like that so that this might help you in solving the assignment. Okay.
Uh,
Yeah. And this is again one of the processing questions, polymer processing questions. Which one of the following properties of polymer are desired during synthesis of polymer? Uh, can you tell me which one of these would be the correct answer?
Low viscosity. Low
Why not?
viscosity,
Yeah,
because
tell me.
of it's easy to synthesize.
Hmm. Uh,
Easy to synthesize and then
and
it's
yeah, yeah, you were right. You were right.
the
You can go on.
melting require less temperature also because of low viscosity.
Uh, yes, you need low temperature to melt it. So since there is low viscosity, handling of the polymer becomes easy. Okay. Why didn't you choose low molecular weight? Any reason for that?
Uh, we lose mechanical strength.
Good.
If we choose, we lose mechanical strength.
Yes, yes, you are right. You're exactly right. We lose mechanical strength if we choose this. So the correct answer for this is low viscosity. Okay. So starting on for sample problems for assignment 3, we have this. Uh, Completely amorphous polymers show only Tg glass transition temperature. Crystalline polymer shows melting temperature, and semi-crystalline polymer exhibits both temperatures. Uh, if I remember correctly, you said that you haven't seen the assignment 3 questions yet, right? Or like you haven't attended the week 3 lectures yet. Am I
Yeah,
right?
yes, sir. Yes, yes,
Yeah.
sir.
So it will be better if you look at this. Okay. So
Okay,
we
sir.
have next.
Next week I try to complete
Yeah, yeah,
that
it's fine, it's
week.
fine, it's fine. Like, anyway, the deadline is by 15th, so make sure you finish it before. Okay?
Okay, sir.
Yeah. So we have completely amorphous polymers. First statement is completely amorphous polymers show only TG, glass transition temperature. So amorphous polymers, so you can see here, right here, there is a temperature versus the modulus graph. Okay?
Okay, sir.
Yeah. So you can see that there is this chart you can see here, stiffness or modulus given in megapascal and temperature in Kelvin. So as you can see, as you keep heating a polymer, it first uh, transitions from glassy state to rubbery state. This zone where it transitions, right? This zone is called the glass transition region. You can see
Okay.
it right here. This the curve on the right hand side. This curve is obtained from an instrument called differential scanning calorimeter. Okay, what this instrument does is it provides a temperature and it puts a polymer or the sample itself through cycles of heating and cooling. Through which what happens is you will be able to figure out what is the melting crystallization temperatures of the material. Okay, so what happens is you can see right here this region right here. This graph is just a magnified version of this one. What happens in glassy state? What is a glassy state? In like at a room temperature, the polymer is somewhat hard and not it's rigid. It's not flexible. As you continue heating it, what happens is it will lose that rigidity. Why? Because the polymer chains are losing the crystallinity and their packing. Because when polymer is at room temperature, all the polymer chains are clumped together. Okay, they are properly
Okay, sir.
entangled. So when the temperature increases, the entanglement gets removed and they start to flow slowly here and there. So that's why this transition occurs. Once this transition occurs, it goes to rubbery state. Rubbery state means it becomes even more flexible. Like initially the polymer was rigid, and once it starts flowing around, it becomes rubbery, and so there is a rubbery flow. Then you can see again we when we go here, this region is the rubbery region. Then as you keep going, what happens is viscous flow occurs. Why? Because here melting is happening. It is forming a melt. Now, before going to the melt, you will see a big peak here. Why did this happen? Because as the polymer is moving from glassy to rubbery state, its crystalline arrangement is going to break. Once the crystalline arrangement is going to break, what happens is the heat starts flowing inside the polymer and there is a big jump here. Is it visible? It
Yes,
is
sir.
visible to you, right? Yeah. So what is happening is we go from glassy state to transition, then to rubbery, and then when this rubbery state occurs, the chains start moving away from each other. It means that the polymer is no longer crystalline. So this is the point which is called the crystalline temperature. Okay, this is called the crystalline temperature, and this crystalline temperature, right? This is the temperature where if you go below it, polymer will show some degree of crystallinity, and if you keep cooling it down, it will form proper crystals. But if you keep increasing the temperature beyond this, it will start melting. As you can see,
Melting.
it
Okay.
starts melting. Okay.
Oh,
And you can see right here. Okay, it's not visible because of all these lines. Yeah. See, you can see heat flow here. Is it visible to you? Heat flow. This y-axis. Heat flow is there, right? Hello, am I audible?
yes, yes, sir. Yes, sir.
Yeah, yeah. So if you can see, there is
Yes.
this is on the y-axis. There is something called heat flow. Now, polymer inherently it does not conduct heat. It does not conduct heat. Okay. So what is happening in crystallization is the moment we reach near crystallization temperatures, the heat flow happens into the polymer because of which there is a big jump. Okay, this big jump happens, and then as it moves towards melting, the heat flow decreases. Why? Because latent state, latent state is happening. It is transitioning from crystal to molten state. So what is happening? That heat is getting used to convert it to a melt form. So this form of it. Okay. So after this explanation, you can see that this statement is true. Why? Because completely amorphous polymers they show only Tg because they are already amorphous. It means that their chains are not organized properly. So they will only show this glass transition state, and then since they never form the crystallinity, like crystalline nature, they won't show crystallization temperature. They will just show a small bump here, and then they will fall into a melting zone. Okay. Then next we have crystalline polymer shows melting temperature and also crystallization temperature. Because since it's a crystalline polymer, its chains are uh, like correctly set into a crystalline pattern. Okay. Then next we have semi-crystalline polymer. Okay. By default, all polymers are semi-crystalline in nature. No polymer can be completely amorphous or it can be completely crystalline. because it's just impossible. That's why all polymers are semi-crystalline in nature, and they exhibit both temperatures, TG and melting and crystallization. Okay, so this answer for this question will be true. Okay, hello, am I audible?
Ah, yes, sir.
Like,
Okay, sir.
yeah, like just keep interacting with me, or else what happens
Uh,
is I might lose track if I just keep like if I keep talking and
yes, sir. Understood, sir.
yeah, okay, good. Okay, so let's move on to the next question. This will actually help you in answering your assignment three questions a lot. Okay, this explanation
Yeah,
you
yeah,
will
yes,
see the
sir.
questions and you might understand. The next
Yes,
thing
yes,
is
sir. Definitely.
yeah. Which of the following statement is wrong for the non-elementary reaction system? Okay, let's see. There is no direct relationship between the rate equation and the stoichiometry of the reactants involved in the reaction. The stoichiometric coefficients are same as the power raised to the corresponding reactant concentration terms used in the rate law. Then the reaction is said to be non-elementary. The third is there are needs of a series of elementary reactions to solve a non-elementary reaction system. We have to assume a series of elementary reactions occurring with the negligible amount of intermediate product formed for a short period of time. So if you analyze these statements, you can see that this statement 3, right? Statement 3 gives us some idea about what is a non-elementary reaction. Now, a non-elementary reaction is a reaction which does not occur in a single step. Occur in a single step, or it forms different intermediates. For your information, this is a energy versus reaction progress graph. So for any reaction to
Okay, sir.
occur, it needs some threshold energy or activation energy from where the reaction can happen. Okay, so
Okay, sir.
as you can see, a complex see this black curve here represents the elementary reaction, which will have just a small single bond, which means that as soon as the conditions are met, the activation energy is achieved and the reaction occurs and the products are formed, reactants and products. Okay. Whereas
Okay, sir.
in a complex reaction, like A A gives C. Now this A gives C looks straightforward, but it's not. It might form B, or it might again revert back to A or something like that. Okay. What this does is it forms a series of reactions which need to be successful for C to form. Okay, and because of this, you can see that there are different bumps occurring. Okay, why? Because
Okay, sir.
this is like forming an intermediate at different positions. That's why it's a complex reaction. Okay, so if you remember the like definition for what is the order of reaction, so you will know that the stoichiometric coefficients, as you can see in the second statement, the stoichiometric coefficients are same as the power raised to the corresponding reactant concentration terms used in the rate law. Then the reaction is said to be non-elementary. But this is not true in case of non-elementary reaction systems. As we just discussed, since A to B is not happening directly and it is happening through a series of other reactions, it won't have a straightforward rate equation. Its stoichiometric coefficients won't match with the uh, reaction scheme itself. That's why the second statement is incorrect in case of non-elementary reaction system. Okay, and rest all you can see that there
Okay,
is
sir.
no direct relationship between the rate equation and the stoichiometry. This is true. This is true. This is just the inverse of this. Then there are needs of a series of elementary reaction. Yes, since A is forming C directly, uh, we can write A forms A star, A star. That's intermediate. Then A star goes on to form B. That's another reactant. Then B goes and forms C. So you can see here, it did not happen like directly. It has gone through a series of two steps. So you would see if you were to draw energy versus reaction progress graph for such a reaction, you would see that there will be variations. That variation, those variations are happening because intermediates like these are formed. Okay, and that's why there is a need of series of elementary reactions to solve a non-elementary reaction system. If you were to map out the activation energy of all the individual ones, they would be this. They would give you like the sum of these will give you this initially. Okay, so that
Okay,
is
okay,
one.
sir.
Yeah. So let's move on to the next question. We have what is the slope of the plot of ln k, that is your rate constant, versus 1 by temperature for a reaction where the activation energy E is positive or temperature dependency of reaction constant given by the Arrhenius equation. Now, Arrhenius equation is the one which you use for temperature-based reactions. Okay? It's like you're understanding, right?
Yes, sir.
Yeah. So what it basically says is that if you increase the temperature, uh, the amount of activation energy required would be less. So we have the ln K versus temperature graph right here. If you know, the Arrhenius equation is given by like this. Uh, Forgive me because I'm not able to draw that properly, but K is equal to K naught e power minus a by RT. So you can see right here, this is the Arrhenius relation. Okay, so if you were to plot ln K, if you were to apply logarithm to this, what would it give you? Ln K is equal to ln K naught plus this term would come down and you would get logarithm of E, natural logarithm of E. Then what this shows is that we are already taking out 1 by temperature here. Okay, and ln K we are taking out right here. And this right here is your intercept. Uh, Sorry, this right here is your intercept. This one right here. That will be your ln A or K naught. K naught or A naught you can take. That is the frequency factor. Okay. When you plot this, the slope which forms here, the slope of this line, okay, that will give you the answer. Now, the slope which forms here is nothing but minus of E by R. This. Okay.
Okay, sir.
Yeah. If you take two temperatures such as 500 and 300, 500, 300, like reaction, like the rate constant decreases quickly. Like see here, this is for 300, this is for 500. If it decreases and then you draw a straight line, you will be able to calculate the uh, slope, which is nothing but your minus E by R. Okay.
Okay, sir.
Then next we have the rate of reaction is a function of which of the following: the reacting material, temperature, concentration, or the type of reaction. Now, if you take a look at this properly, you will see that reacting material. What is reacting material? Reacting material means anything which you start with, like you have like like something like sodium. If you just keep it exposed outside in the atmosphere, what will happen? It will just react with air or moisture, and it will uh, produce a lot of heat. So it's reacting by itself. So reacting material, yes, the rate of reaction will depend on that and what kind of material it is and what kind of condition it is going through. Okay, that is one thing. And next we have temperature. We just now saw the entire definition and how the Arrhenius equation works. So we can say that temperature also is a big factor. Okay, so reacting material and temperature, these two main factors. The next is concentration. Now, if you have seen a rate equation, you would say that it goes like this: Ca by dt to Kc. Now you can see that there are concentration terms here and here. So which means that concentration is also a very important part in determining the rate of reaction. Okay.
Okay, sir.
Yeah. But Then we come to the last one, this one. Now, the type of reactor. Type, the type of reactor used here wouldn't affect the reaction as much as these would. What type of reactor does is it changes the residence time. Residence times mean the amount of time the reactants spend inside experiencing these conditions. Okay, reactor is like a space where you carry out the reaction. It's not like inherently taking part in the rate of reaction itself, but it's just like a space where the reaction is being carried out. Okay, it's kind of providing a residence time for your reaction to occur and then product to form. That's right. So these three would be the answers: reacting material, temperature, and concentration. Because this is not
Okay, sir.
inherently taking part in the reaction itself. Okay. Uh, then let's move on to the next question. We have choose the correct option from the following statement. In the Arrhenius law, the reaction rate constant is directly proportional to the temperature. In collision theory, the reaction rate constant is directly proportional to square root of the temperature term. In transition state theory, the reaction rate constant is directly proportional to temperature term, and collision theory is based on kinetic theory of gases. So, have you heard about the collision theory? You might have heard about it. Collision theory or
Uh,
kinetic theory of gases. Kinetic theory of gases, you might have heard about this, right?
yes, sir.
Uh, uh, kinetic uh, kinetic theory of gases explains how gas molecules behave, like what are the attractive forces, repulsive forces, and how they exert pressure in the vessel in which they are contained, and what do the collisions between those gas molecules, how they are mapped out. Okay, based on that, your collision theory is made. Now, for a successful reaction to occur, particles have to interact with each other. Particles have to interact with each other to give birth to the products. Okay. Now, if A and B are far apart, nothing is going to happen. They need to come together close. Okay. Like they have to interact with each other very close enough that will so that they can form an intermediate, which will then turn to your product. Okay. Now, since collision of the molecules itself is a big factor, and uh, this theory is based on the kinetic theory of gases, which defines how gas molecules behave inside a closed container and how the interactions between the individual or different gas molecule mixtures shows how the kinetic energy of the gas molecules changes due to the collisions. So based on that, this theory is also collision theory. Okay, then which means that this is a correct statement.
Okay, sir.
Okay, then we have transition state theory. The reaction rate constant is directly proportional to temperature. As we have just seen here uh, in the explanation of Arrhenius law, that the transition from uh, some specific threshold to reach the activation energy, that defines your transition state theory. And in during this point, the reaction rate is proportional to the temperature term. So if you increase the temperature, your activation energy would come down, and then the reaction would uh, progress more easily. Okay, so here this is that. Then next we have uh, in the collision theory, the reaction rate constant is directly proportional to the square root of the temperature. Now, in collision theory, since it's based on the kinetic theory of gases, you see that in collision theory, whenever you define the collision of two gas molecules, you are going to use their mean square root, uh, mean square of the molecules, and the distance between them, RMS, root mean square. Okay, so that would define how the collision is happening. Okay, and corresponding to that relation, the collision theory, the reaction rate constant is directly proportional to the square root of the temperature. Okay, so root square root of the temperature term. As you can see that the temperature term changes with respect to the square root, and then the collision of the molecules either decreases or increases, because of which the reaction rate constant is affected, proportional. So even this is correct. And the last one is the Arrhenius law. The reaction rate constant is directly proportional to the temperature. Now, we have seen right here that it's not directly proportional to the temperature, and there are a series of other terms which come in the middle, and it's not directly proportional to the temperature. So the statement one here is